Dear students, now we shall discuss about the preparation of alcohols from alkenes, secondly from carbonyl compounds, and from the Grignard reagents. Here we have the discussion on the preparation of alcohols from alkenes, carbonyl compounds, and Grignard reagents. Okay. Yes, first we shall discuss about the preparation of alcohols from alkenes. Okay, yes, from alkenes we can easily convert these compounds into alcohols either by acid catalyzed hydration. By acid catalyzed hydration. Yes, and it is a type of electrophilic addition reaction. It is a type of electrophilic addition reaction. Okay, let's see what is this acid catalyzed hydration and why it is called as electrophilic addition. Okay, let's consider the general reaction for this. Okay, C double bond C. Alkene means it must have C double bond C. Okay, yes. Here we are going to add the H2O onto that alkene in the presence of an acid. Here acid is represented as H plus ion. Okay, acid, it is acting as a catalyst, and so therefore it is called as acid catalyzed. Okay, hydration, that is addition of water. So this reaction is called as acid catalyzed hydration of alkenes, which gives the alcohols, for example, H2O is nothing but H plus ion and OH minus ion. If one of the H plus ion attacks this carbon, OH minus will attack this carbon. Okay, so therefore you will get hydrogen here and single bond C. During the addition reaction, the double bond will be converted into the single bond. Okay, so now we will get the compound like this. Now this is an alcohol. This is an alcohol. See, now why it is called as an electrophilic addition reaction? Because when you consider the H2O structure as this, okay, and here we have got a double bond. Here the sigma bond is present and pi bond is present, where in this pi bond the pi electrons are loosely bound electrons. These will first take up this H plus ion. So it looks like the attack of H plus ion first onto the carbon atoms. Okay, therefore this is called as electrophilic addition, and later the nucleophile OH minus will attack on the another carbon. Okay, but first which one is attacking? The electrophile H plus ion is attacking, therefore it is called as a electrophilic addition reaction. It is called as a electrophilic addition reaction. Okay, let's see the mechanism of this reaction. It is very important. Let us understand the mechanism of this reaction. It is very important for annual examination also. It involves 3 steps, and the step 1 is electrophilic addition. So what is attacking first? The electrophile is attacking on the double bond. Okay, so first step is electrophilic addition. Electrophile, what is the electrophile here? H plus ion, or we can consider the hydronium ion. Electrophile H3O plus. Okay, electrophile attack on the alkene, to give carbocations. Yes, let's see that reaction. Okay, yes, when you have this C double bond C, okay, here the electrophile H3O plus ion will attack. How this H3O plus ion has come? when the H2O, where O is having two lone pair of electrons, is treated with an acid, that is H plus ion, it makes a bonding, so gives H3O. Okay, and here you have got the lone pair of electrons as it is, and due to the bond formation between this O and H, it loses one lone pair, so it got a positive charge. And here you can represent it like this, or you can represent this as H3O positive charge. Okay, usually we write the hydronium ion like this because the charges are kept on the uh, top end, okay, as a superscript. Okay, now that electrophile hydronium ion, what is this called? Hydronium ion. This is called as hydronium ion. Okay, yes, the hydronium ion attacks on this alkene. Okay, how it makes bonding? Here one of the pi bond moves, okay, and takes the hydrogen, okay, and becomes this. During the addition reaction, the double bond is converted into the single bond, and here it forms this carbocation plus H2O. Now, due to the loss of that proton H plus ion, the oxygen atom gains back its lone pair of electrons. Okay, now it will have two lone pair of electrons as it is. Now, this is called as a carbocation. This is called as a carbocation. Okay. Now, in the second step, you can see the attack of H2O. H2O here acts as a nucleophile. Okay, step 2 is nucleophile attack. What is the nucleophile here? H2O. Okay, nucleophile H2O attack on carbocation, gives the protonated alcohol. Let's see that. Here we have the carbocation, okay, and to this the H2O, it is a nucleophile is attacking. Okay, always keep in mind that the electrons will move. Okay, like this it will move and gives the protonated alcohol. This as OH2. Here also again the oxygen is making use of one lone pair of electron, and due to the loss of one lone pair of electron, it gets a positive charge. Okay, and one more, the lone pair of electron will be present. Okay, now this is called as a protonated alcohol. Okay, now this is unstable molecule, that is why it undergoes deprotonation. The step 3 is called as deprotonation. Deprotonation is nothing but removal of proton. Here proton means the H plus ion. Okay, and from this molecule, that is protonated alcohol, one H plus ion comes out. Then you can see the OH group on this. Now this is called as an alcohol. Okay, see, in the entire reaction mechanism on this compound, you are observing there is a H plus ion, that it is hydrogen on this carbon, OH minus ion on this carbon. As I already told you that H2O considered it as H plus and OH minus ion. First the H plus ion attacks on this carbon and OH minus attacks on this carbon. Now finally you got that H on this carbon, OH on this carbon. Now this is the representation of the alcohol. This is a general reaction mechanism for the conversion of the alkanes to alcohols. Okay, it involves three steps and the mechanism is called as electrophilic addition because the electrophile first attacks. Okay, now step 1 is electrophile, that is H3O plus ion attack on the alkene to give the carbocation. Carbocation is the species where carbon is carrying the positive charge. Okay, and the second step is nucleophile, that is H2O acts as a nucleophile here due to the presence of lone pair of electrons on the oxygen. Okay, now the nucleophile attack on the carbocation gives the protonated alcohol in this way. Okay, and this is unstable, therefore it undergoes deprotonation. It means the removal of proton. Okay, so this is all about the acid catalyzed hydration of alkenes to give the alcohols. Dear students, now let us consider an asymmetrical alkane from which we can prepare the alcohols. So what is so important to consider the unsymmetrical alkene? Let us know first what is unsymmetrical alkene. See, here we have the propene. It is an example for unsymmetrical alkene. Here when you consider this double bond on right hand side of this carbon, on right hand side of this double bond we have one carbon, and on left hand side of this double bond you have two carbon atoms. This difference in the number of carbon atoms on either side of the double bond results in unsymmetry or asymmetry. Okay, now when you do the acid catalyzed hydration of this propane gives you a stable product after obeying the Markovnikov's rule. Let us understand how the process takes place. Yes, when propane is treated with the water in the presence of the H plus ion. Okay, let us consider the H2O as H plus ion and OH minus ion. So H2O is a combination of H plus ion and OH minus ions. Now, as you know already, it takes place through the electrophilic addition. Means firstly, the H plus ion will attack on this propene. Okay, and how this follows, the H plus ion attacks either this carbon or this carbon. It is governed by the Markovnikov's rule. So let's take that rule, Markovnikov's rule. Okay, so what is this rule? Okay, it states that during the addition of unsymmetrical reagent to the unsymmetrical reactant, the negative part of the addendum. So what is the negative part here? OH minus N. Negative part of the addendum gets attached to the doubly bonded carbon with less number of hydrogens. So these two are doubly bonded carbons. This has got one hydrogen, this has got two hydrogens, and this rule states that negative part of the addendum gets attached to the doubly bonded carbon with lesser number of hydrogens, and the positive part gets attached to the double bonded carbon with a higher number of hydrogen atoms. Okay, in this way, if the attacks takes place, then this will be the product. Okay, this is the product. So what is the name of this compound? Propan 2OL. Propan 2OL, because OH group is present on the second carbon. If you number this as 1, this as 2, this as 3, so propan 2OL is the IUPAC name. Means here the product obtained after following this Markovnikov's rule is a stable and major product. It is a stable and major product. Okay, what happens if you don't obey this rule? Okay, if you interchange these attacks. Okay, for example, H plus ion attacks on this, consider H plus ion attacks on this. Okay, and you will get the product that is CH3, CH2, CH2OH. This is against to the Markovnikov's rule. This is against to the Markovnikov's rule, and it is a unstable product. So what is this compound? This compound is propan 1OL. Propan 1OL. This is unstable. Therefore, you can say it as a minor compound, and it is unstable from this method. Okay, isn't it? Okay, so that is why you need to remember the Markovnikov's rule. In this situation, you have to follow the Markovnikov's rule. Okay, yes, let us consider the preparation of alkenes by hydroboration oxidation method. By hydroboration oxidation method. Here, as the name suggests, there are two processes taking place one after the other. That is, first hydroboration will take place, okay, and the oxidation takes place. Yes, let us consider the same molecule propene to understand this method. Yes, take the 3 moles of propene, okay. Take the 3 moles of propane and treat this propane with the diborane. Here diborane is B2H6. Okay, diborane is B2H6. For our convenience, I am taking 1 unit, 1 BH3 unit from that B2H6. So this process is called as a hydroboration. Here, the addition of borane to the propene is called as hydroboration. Okay, means you will get an addition product. Okay, yes, let's see that here there are 3 hydrogens in the BH3 unit. Those will attack on this carbon. Okay, so 1 hydrogen attacks on 1 propene at this carbon. Therefore, you have 3 hydrogens and 3 propene molecules. In this way, you will see the adduct, that is CH3, CH2, CH2, 3 times and boron. Okay, see here, all the hydrogens are attached to this carbon. Okay, and now this compound is called as trialkyl boron. Okay, trialkyl boron. Okay, now this is an adduct. Adduct is nothing but addition product. Adduct is nothing but addition product. Okay, now it is a step called as hydroboration. It is a step called as hydroboration. Yes, let's see the oxidation of this trialkyl boron. Okay, yes, take that trialkyl boron, CH3, CH2, CH2, 3 times boron, okay, and oxidize this using hydrogen peroxide in the basic medium, that is OH minus. What is this OH minus stands for? It stands for the basic medium. Here you may take NaOH as the base, okay, and in the presence of H2O, what happens here, the attack will take place like this. In this H2O, you may consider one part of OH attacks to this and another part attacks to this. So you will get, you have to take 3 moles of H2O2. You have to take 3 moles of H2O2. Therefore, 3 OH units attacks to this and 3 OH units attacks to this. So therefore, you will get 3 moles of CH3, CH2, CH2, OH, and this will be BOH 3 times. Now this is called propan 1-OL. It is the major product here and a stable product. Okay, this is a major stable product in this method. Okay, and what is the byproduct? Byproduct is called as boric acid. It is called as boric acid. Okay, it is all about the preparation of alcohols from two methods. One is acid catalyzed hydration of alkenes or by hydroboration oxidation of alkenes. Here there is a major difference when you take the propane and if you subject it for acid catalyzed hydration. Propan 2-OL is the stable and major product and it is accordingly the Markovnikov's rule. Okay. Yes, when the same molecule is subjected for hydroboration and oxidation, you will get propan 1-OL as the major and stable product. Here, the difference lies with the mechanism of the reaction. Here, the difference lies with the mechanism and reagents used to prepare the alcohols. And here, in this method, that is hydroboration and oxidation of propane, gives the excellent yield. The propan 1-OL obtained will be having the excellent yield. Means if you take the 100 moles of the propane, almost more than 90% of the product you will get. Means 90% of the reactant molecules will be converted into the product side. Hence it will be a good in getting the product. So that we call as yield. Okay. Dear students, now we shall discuss about the preparation of alcohols from carbonyl compounds. So we know that carbonyl compounds are the compounds containing C double bond O group Okay, here we have 4 types of carbonyl compounds. One is aldehyde, the second one is ketones, the third one is carboxylic acids. Carboxylic is a different, but also it has a C double bond O group and esters. Okay, let us try to see the conversion of these carbonyl compounds into the alcohol. Here it requires a reducing agents. Okay, and the process is called as a reduction process. Okay, let us discuss about the reduction of carbonyl compounds into alcohols. Yes, first we shall consider the reduction of aldehydes. Reduction of aldehydes will give you the primary alcohols only. Okay, yes, reduction of aldehydes to primary alcohols. Let's see that. Okay, yes, here we can use the catalytic hydrogenation method, that is using the hydrogen molecules or hydrogen gas in the presence of nickel, platinum, palladium as catalyst. Okay, let us see the general reaction for this. Okay, we have RC double bond OH. This is the representation of the aldehyde. Now, when hydrogen gas is passed over this aldehyde in the presence of the catalyst like platinum, palladium or nickel, any of these, okay, gives the alcohol. How it gives? One of the hydrogen will be attacked on this oxygen and another one will be on this carbon. So you will get RCOH, H. This H, one hydrogen is going to attack this carbon and there is already one carbon. So it is nothing but RCH2 group. Okay. Now this RCH2OH, okay, here you may write this like this also, RCH2OH. See here OH is present on this carbon, it is linked to only one another carbon in this alkyl group. Okay, here R is alkyl group. Okay, now OH group is present on this carbon is linked to only one other carbon in this alkyl group, so therefore it is called a primary alcohol. It is called a primary alcohol. Say the reduction of aldehydes will give you only the primary alcohols. For example, let's consider the ethanol. Here pronunciation may be same. Okay, CH3, CHO. Here I am pronouncing this molecule as ethanol, but when you look at the name of this compound, here it is an AL, it refers to the aldehyde. It refers to the aldehyde. So here the spellings are most important. When you write OL, it is an alcohol. When you write AL, it is an aldehyde. Okay. Okay, now let us consider the catalytic hydrogenation of this ethanol. Okay, that is addition of hydrogen in the presence of this catalyst. Okay, as platinum, and it gives you the CH3, CH2, OH as the product. So it is ethanol. Here, look at the difference between the spellings. AL aldehyde, OL alcohol. Okay, now it is a primary alcohol. It is a primary alcohol. Okay, because the OH containing carbon is linked to only one other carbon. Okay, yes, similarly let us consider the reduction of ketones. Reduction of ketones. Yes, here, let's take the general reaction for reduction of ketones like this, RC double bond O R dash. Here R and R dash may be same alkyl groups or different alkyl groups. Okay, here we need to have a reducing agent like sodium borohydride. Okay, like sodium borohydride, it only supplies the hydrogens. Okay, no need to add the hydrogen gas again. Here there is a bulk number of hydrogen atoms. Now this is called a reducing agent. Reducing agent, or you can call it as reductant. So sodium borohydride is a reducing agent which reduces the ketones. What is this? Ketone. Okay, to the secondary alcohol. To the secondary. How? One of the hydrogen will be attacking on this, another hydrogen will be attacking on this. So you will get RC R dash and one hydrogen here, another OH group here. Okay, like this it is a secondary alcohol because the functional group containing carbon is linked to two other carbons. Okay, it is a secondary alcohol. In the same way, we shall consider the reduction of carboxylic acids to the primary alcohols. Yes, let's have the general representation for this. We have RC double bond OH. This is called the carboxylic acid. Okay. Here R may be any alkyl group, and here it requires a strong reducing agent such as lithium aluminum hydride. It requires a strong reducing agent such as the lithium aluminum hydride. Okay, it is somewhat expensive also. It is expensive also. So what is this? It is a stronger reducing agent, that is lithium aluminum hydride, and it is expensive. Okay. Yes, here when the carboxylic acid is treated with this lithium aluminum hydride, or you may take the diborane also, this will convert the carboxylic acids to the primary alcohols like this RCH2OH. Okay. Yes, now we can convert the carboxylic acids to primary alcohols either by using lithium aluminum hydride or by using diborane followed by the hydrolysis. Okay, it gives the same compound, that is a primary alcohol. Okay. Yes, so these are the two ways to convert. Let's have an example. Okay, for example, I have acetic acid, that is CH3COOH. So what is this called? Acetic acid. In the IUPAC name, it is called as ethanoic acid. Okay. Yes, when you add lithium aluminum hydride or diborane B2H6 followed by hydrolysis, you will get this CH3CH2OH. See, this carbonyl carbon will be reduced to this alcohols. Okay, so now this is called ethanol and it is a primary alcohol Yes, let's consider the other methods. Okay, that is see, because here the lithium aluminum hydride is most expensive. That is why we have another method to convert these carboxylic acids to primary alcohols by converting the carboxylic acids to esters. Okay, so we shall consider the other method, that is the fourth method, reduction of esters to primary alcohols. Okay, let's consider that. Okay. Yes, reduction of esters. How we get the esters? Again from the carboxylic acids only. Okay. Carboxylic acids are converted into the esters. Esters are converted into the primary alcohols. Yes, let's take the general representation here. When carboxylic acids are, what is this? Carboxylic acid when treated with the alcohols, okay, I am taking R dash OH. Here this R and R dash may be same or different. Okay, when carboxylic acids are treated with alcohols in the presence of an acid, okay, it undergo esterification to give RCOOR dash. It is called as ester. Okay, with the release of water molecules. Okay. Yes, and further reduction of this ester. Okay, using the catalytic hydrogenation, that is addition of hydrogen in the presence of platinum, nickel or palladium as catalyst. It gives RCH2OH plus R-OH. Here you are getting the primary alcohols. This is one type of primary alcohol. This is another type of primary alcohol. So in this method, you are getting the mixture of primary alcohols. And you need to separate these two again using some techniques. Okay. Yes, the conversion of carboxylic acids to ester in this method is called as esterification. That is when carboxylic acids are treated with the alcohols in the presence of an acid, use the ester. This method is called as esterification. Okay, and the reduction of these esters will give the mixture of alcohols. Okay. Dear students, now we shall discuss about the preparation of alcohols from Grignard reagents. You know what are Grignard reagents? These are organometallic compounds. Here, organic part is R, that is alkyl, and the metallic part is magnesium. So this is called a organometallic compound, and particularly it may be called as alkyl magnesium halides. And here you may also take the aryl group, aryl magnesium halides. Okay, let us see how to convert these Grignard reagents to the alcohols. Here it follows a nucleophilic addition reaction first, gives the adduct, and followed by the hydrolysis. Okay, let's take the general representation for this reaction. Okay, yes, take the carbonyl compound. See, you have to again use the carbonyl compound. It may be an aldehyde or maybe a ketone. Okay, let's take that carbonyl compound like this, C double bond O. So what is this C double bond O? It is a carbonyl compound. It is a carbonyl compound. Okay, yes, when this carbonyl compound is treated with the Grignard reagent, that is RMGX, here we have to consider two parts of this Grignard reagent. The alkyl part is electron rich, so therefore this is delta minus, and this metallic part will be having delta plus. Okay, and here in the carbonyl compound we have a carbonyl carbon and carbonyl oxygen. You know that oxygen is most electronegative element, so it will take these pi electrons onto this. Means it will pull the electrons towards itself and it slightly becomes delta minus, and due to loss of electron density on this carbon it becomes a delta plus. Okay, so what you can observe when these two are treated together, okay, definitely due to the opposite forces these will attract each other. Okay, so here the delta plus carbon will be attracted by the alkyl group. Okay, here R minus, that is alkyl part, will join the carbonyl carbon. Yes, it will join the carbonyl carbon. You will get like this, and this negative part oxygen will take that Mg, so it will be OMgX. Okay, now this is called the addition product or an adduct. Okay, so this is an adduct, and how the reaction is triggered. The reaction is triggered because of the approach of the alkyl group onto this carbon first. Firstly, the nucleophile is attacking on this carbon, so this is called a nucleophilic addition. Okay, now after getting this, if you do the hydrolysis, that is addition of water to this, so what happens? Water is nothing but two parts, like having the H plus ions and OH minus ions, and at this case, at this place, the bond gets broken. It takes the H plus ion and it takes the OH minus ion. Okay, let's see what is the product after that hydrolysis. Here you will get OH, and here it is already R. So after that the remaining part is H plus ion is taken already and OH minus is present, that will be linked to the magnesium. So you will have this magnesium, OH and X. This is the byproduct. Okay, this is our compound, that is alcohol. Okay, this is the general representation. Okay, now this is a nucleophilic addition mechanism. It is very important because here carbonyl carbon is electron deficient. This alkyl part, nucleophilic part, is attacking on this. That is why it is named as a nucleophilic addition mechanism. Okay, let us consider some examples here. Okay, here we have to have a keen observation that when a first aldehyde, so what is the first aldehyde, first member of the aldehyde? Methanol. Okay, yes, you take the methanol on treating with the Grignard reagent, methanol with RMGX. I'll take simply RMGX. Okay, methanol with RMGX gives the primary alcohol. Okay, let's see what happens. See, I am taking methanol, Al, it stands for aldehyde, okay? Yes, C HC double bond OH. You may take this as HC double bond OH and RMGX. Here R may be any alkyl group, okay? From this R will attack onto this carbonyl carbon, as I already told that it is having a less electron density, that is delta plus, and it is delta minus. That negative alkyl part will attack onto the carbonyl carbon. So so this alkyl part having rich in electron density attacks at the carbonyl carbon, which is having a electropositive character. So it gives the adduct like this. R gets attacked here, you have OMGX. Here X is an halide, it may be the Cl or Br. Okay, yes, when you perform the hydrolysis on this, you will get the alcohol like this, RCOH plus MgOHX. So what is this alcohol? It is a primary alcohol. How can we say that it as a primary alcohol? Because the OH is present on this carbon, it is linked to only one other carbon of this alkyl group. Okay, now from this you understood that when methanol, that is an aldehyde, is treated with the Grignard reagent, you will get a primary alcohol as the final product. Okay, see here you cannot say which is the particular alcohol you get. That is all dependent on the what alkyl group you use. If you take R as CH3, hence you will replace this R with the CH3, it will be CH3CH2OH, then it would be the ethanol. Okay, like that the final particular product is dependent on what type of Grignard reagent you are going to use. Okay, and let's see other aldehyde. Okay, that is in the second you can have other aldehydes with RMGX gives the secondary alcohols. Say in the aldehydes, the first member gives the primary and the second members and following members will give the secondary alcohols. Yes, let's see that the higher aldehydes are represented like this. Okay, here R is equal to alkyl group. Okay, now when these aldehydes are treated with the Grignard reagent, it undergoes nucleophilic addition. Here electron rich alkyl part gets attached to the electrophilic carbonyl carbon. So therefore you will get RCH ROMGX, like this. This is an adduct. Okay, when it is hydrolyzed, that is when H2O is added, you can see the breakage of the bond here. This will take the H plus ion and it becomes RCOH OH plus R here, H here. See here, the functional group containing carbon is linked to two other carbons. So therefore it is called as a secondary alcohol. Okay, and the byproduct will be the same, that is MgOHX. Okay, here you may use X as Cl or Br. Why can't we use the fluorine? Because it is most reactive, it won't give the desired product. Okay, why don't we use the iodine? Because it is a heavy molecule, heavy ion, and it undergoes the reactions very slowly, and there is a chance for the reverse reaction. That is why we do not prefer the fluorine and the iodine. Because of the disadvantages of these two ions, we don't use this. We follow or we prefer this chlorine and bromine, and it gives the desired product. Okay, now let us see the conversion of ketones. So far we have discussed the reaction of Grignard reagent with the methanol and other aldehydes. See, when methanol, if you use, you will get primary alcohol, and other aldehydes use the secondary alcohols. Yes, now let us consider the third one, that is ketones. Okay. Okay, when you use the ketones, when ketones treated with Grignard reagent, gives the tertiary alcohols, Yes, let us see how it gives the tertiary alcohols. Yes, ketones are represented like this: RC double bond O R dash. Okay, here R and R dash may be same or different alkyl groups. Okay, take the Grignard reagent again. Let's mark it as star or star. Okay, yes, here this is the electron rich alkyl group, and this is electrophilic carbonyl carbon. Okay, this attacks on this, so you will get RC R dash, RC R dash, and R star. Okay, and here you may take this as OMGX. Okay, and R star. Okay, yes, here this is an adduct. Okay, when it is hydrolyzed using H2O, yes, it will give the breakage of bond here, and RCOH R star R dash. Okay, and there will be the byproduct as well. Okay, now you can see the functional group containing carbon is this. It is linked to the three other carbon atoms. Okay, hence it is a tertiary alcohols. Okay, so in this way you can see the conversion of carbonyl compounds into alcohol using Grignard reagent.